Now we'll begin chapter 4. In this chapter, we're going to talk about chemical reactions that occur in solutions. And in addition to that, we'll do some stoichiometry for these chemical reactions. So once again, we're going to get additional practice by doing stoichiometry problems in this chapter here. We'll begin chapter 4 by talking about the dissolution of substances in water to produce what are called aqueous solutions. And we'll also discuss electrolytes and strength of electrolytes. So we'll begin with a lot of definitions here. First, we'll define what a solution is. A solution is defined as a mixture of two things, one called a solute and one called a solvent. And I'll define what those terms are in a few moments, but we'll just say a solution is a mixture of a solute and a solvent. An example of a solution might be a saltwater solution, right? Like brine, or like ocean water is a saltwater solution. Okay, now let's define what solute and solvent are. So solute is the substance that is being dissolved. That is the minor component in the solution. So in a saltwater solution, the salt would be considered the solute because that's the minor component. That's what's been dissolved. The solvent is whatever substance is doing the dissolving. This is the major component in the solution. So in our saltwater solution, the water would be the solvent. In any aqueous solution, water is the solvent. That's what the term aqueous solution means. It means that you have a solution for which water is the solvent. Next, we'll talk about dissociation. So dissociation is the separation of a soluble ionic compound into its ions, meaning that if you have a soluble ionic compound dissolved in water, it will dissociate or break up into its constituent ions. For example, let's take a look at the dissociation of calcium chloride when it dissolves in water. We start with our calcium chloride, CaCl2, and then we're going to say that it breaks up to form our products, and you're going to break it up into the ions. So what are the ions in calcium chloride? We have the Ca2 plus ion, and we also have the chloride ion, which is Cl minus. Then we have to balance this equation for mass. Because we have two chlorides on the left side of the equation, we have to have two chlorides on the right-hand side of the equation. So I'm going to put a 2 out in front to balance the equation. This is the dissociation reaction. Be very careful when you're writing dissociation reactions. Make sure that you're always breaking an ionic compound up into its ions. I do not want to see something like this. CaCl2 goes to Ca2 plus and chlorine gas. So be aware of that. If you write Cl subscript 2, that indicates that you're doing elemental chlorine gas. And this is not what you have in calcium chloride. You have chloride ions, Cl minus ions. So it's not like this. And it's a good thing that it's not like this. Because if it were, that would mean that when you dissolve calcium chloride in water, you would produce chlorine gas, which would kill you. This is not what happens. This is the reaction that occurs. You break it up into its ions. That's why it's so important to really understand the concept of determining the ions that are present in an ionic compound, something that we discussed back in chapter 2, so you can review that if you'd like. We'll take a look at a second example here. We're told 1 mole of sodium phosphate is dissolved in water. We need to determine how many total ions will be in the resulting solution, and you're given what the formula for the phosphate ion is to help you determine what the formula of the compound is and to help you answer this question. Do you make 1, 2, 3, 4, or 5 moles of ions? Write out the dissociation reaction, figure it out, and on the other side of the quiz question, we'll go over the answer together. Once again, we're dissolving an ionic compound into water, and so we should write out the dissociation reaction. We begin by writing what the formula is. We have sodium phosphate, so sodium is Na plus, and phosphate is PO4 3 minus. So those combine to make Na3PO4. That's balanced for charge. So our dissociation reaction will be Na3PO4 breaks up to make our ions of Na plus and the phosphate ion. Then you have to balance the equation for mass. So on the left side of the equation, you have 1 phosphate, and on the right-hand side, you have 1 phosphate, so that's good. On the left side, you have 3 Na plus ions, and on the right side, you only have 1. So we've got to multiply the Na plus by 3 to balance that. And now this equation is balanced. So let's now figure out what the answer to this problem is. We have 1 mole of sodium phosphate that we begin the problem with, right? The coefficient of 1 is implied here. That's going to break up to give us 3 moles of Na plus 1 mole of phosphate altogether, that gives us 4 moles of ions total. Very important to think carefully about what equations are telling you in words. What this equation tells us in words is that 1 mole of sodium phosphate breaks up to make 3 moles of Na plus ion plus 1 mole of phosphate ion. 4 total moles of ions here. The answer is D. Next, we'll talk about acids and bases. And there are a lot of different definitions of acids and bases, and you'll see several of them as you go through the entire general chemistry series. But for right now, the definition of acids and bases is as follows. We define, for now, acids are any substance that would increase the amount of H plus ions in solution, and bases are any substance that would increase the amount of hydroxide ion in solution. Additionally, we can talk about the relative strength of acids and bases. So we define a strong acid or a strong base as being something that dissociates or breaks up 100% in solution. Examples of strong acids would be substances like HCl or HBr, and there are a few other examples of strong acids. But HCl is a strong acid, meaning that when it's dissolved in water, it completely breaks up 100% of the way into H plus ions and Cl minus ions. And in doing so, that increases the concentration of H plus ions in your solution. The same can be said about HBr. Examples of strong bases are things like sodium hydroxide or barium hydroxide, and there are many others as well. Sodium hydroxide is a strong base. If you were to dissolve it in water, it breaks up 100% into Na plus and OH minus ion. And in doing so, you increase the amount of OH minus ion in solution. That's why this is a base. In contrast, weak acids or bases are substances that dissociate less than 100% in solution. Some examples of weak acids would be hydrofluoric acid or acetic acid, which you also know as vinegar, and there are many others that you're going to study a lot when you get to the chapter on acids and bases in Chem 1B. But HF, for instance, breaks up, but only about 1% of the way into H plus and F minus ions. 99% of the HF molecules you have in a solution remain as HF. They do not dissociate. But only 1% do. That's why we say it's a weak acid, because it doesn't fully dissociate 100% of the way. Some examples of weak bases might be things like ammonia or NH3. And then there are many other examples. And to see why ammonia would increase the concentration of hydroxide ion in solution, that's something that you'll have to look at another definition of acids and bases called the Bronsted-Lowry definition, which you'll learn about in more detail when you get to Chem 1B. Right now, this is just about establishing the definitions of these terms, because these terms will be used later on in this chapter, and they'll be used a lot through the rest of Gen Chem. So make sure that you know what all these definitions are here. We could put a lot of these ideas together and introduce now the concept of electrolyte strength. An electrolyte is any substance that dissociates into ions in solution. We would consider a strong electrolyte as being any substance that breaks up completely 100% of the way, forming lots of ions in your solution. Examples of this would be any soluble ionic compound, any strong acid, or any strong base, because in all of these instances, the substance will break up 100% of the way in solution to make lots of ions in solution. In contrast, weak electrolytes are substances that do dissociate, but only to a small extent, like weak acids and weak bases, for instance. I'll remind you, like in the case of HF, which is a weak acid, it does dissociate to produce ions, but only 1% of the HF molecules dissociate. The other 99% remain as molecules, as HF molecules. There are also soluble substances called non-electrolytes, and these are substances that dissolve but do not break up into ions. And examples of this would be molecular or covalent compounds. In the case of a molecular or a covalent compound, you don't have ions, right? You have covalent bonding. And as a result, when this dissolves into solution, it's not going to be able to break up into ions because you don't have ions in the compound. It's covalently bound. So in this case, you have something that is soluble but does not produce ions in solution. And as such, we call it a non-electrolyte. Electrolyte strength is telling you how many ions you have in your solution, essentially. In a few moments, we're going to take a look at a demonstration that's going to allow us to test the electrolyte strength of various solutes that are dissolved in water. And this test is going to be done by placing an aqueous solution into a beaker and then putting a light bulb into the solution. The wire that's going to carry the electricity to the light bulb is split like this. And so in order to turn the light bulb on, you have to be able to complete the circuit. To complete the circuit, you have to have these probes immersed in a solution that conducts electricity. Solutions that conduct electricity will have lots of ions. They're going to be solutions that contain strong electrolytes. And so when you dip the probes into a solution of strong electrolyte, that is to say a solution that conducts electricity very well, what you'll see is that this will complete the circuit and allow the light bulb to shine very brightly. In contrast, if you were to dip the probes into a solution that contains a weak electrolyte, you will have some ions, and so there will be some conducting of electricity, but not nearly as much as when you're dealing with a strong electrolyte. And so as a result, you will get the light bulb to come on, but it's going to shine fairly dimly. And if you were to dip the probes into a solution that contains a non-electrolyte, then the solution does not conduct electricity at all. And as a result, you will not be able to complete the circuit and the light bulb will not turn on at all. So in a moment, you're going to see a demonstration that will show different solutions and you'll be able to see the differences in their electrolyte strength and their ability to conduct electricity. All right, in this demo, we're going to test electrolyte strength. What I have here is a light bulb and the incoming power cord has been split. In order to complete the circuit, I have to immerse this in a solution that contains something conductive, meaning it has to contain ions. We have to put it in an electrolyte solution. I'll start with deionized water. What do you think is going to happen in the case of deionized water? As the name implies, deionized water contains no ions, and so this solution does not conduct electricity and the light bulb does not turn on. What if instead I looked at tap water? Are there ions in tap water? Yes. And what sort of ions might you expect to find in tap water, right? We know that there's fluoride that's added to tap water. We know that if you have really hard water, like we do here in Santa Barbara, there's going to be some minerals, right? There's going to be some things like calcium and sodium in there. Hopefully there's no lead, but there are going to be other metals, right? Like calcium and sodium and stuff like that. And so because we do see that there are some ions in tap water, we do see that the light bulb glows. Now, it's not glowing very brightly, but it does glow a little bit, indicating that tap water does conduct electricity to some small extent. You can consider this a weak electrolyte. Now, to compare this to what you would expect to see with strong electrolyte, let's take a look at a hydrochloric acid solution. So I'm just going to rinse my electrodes here to rinse with DI water, and then I'm going to put this in a solution of hydrochloric acid. And what we see is that the light bulb comes on very brightly. This is way brighter than what you saw in the case of the tap water, right? Just to go back for a second to compare a weak versus a strong electrolyte. And you have a lot of ions versus not very many. That was HCl, and this was the tap water, right? Big difference there because the HCl solution has lots of ions. All right, next what we can do is take a look at a solution of vinegar, which contains acetic acid. Acetic acid is a weak acid, so we expect this to be a weak electrolyte, and sure enough, that's what we see. The light bulb does turn on because the solution does conduct some electricity, but not a lot, and because there just aren't as many ions as there are in the case of HCl. So it glows, but it glows kind of dimly. All right, we'll rinse this off and go on to the next one. Next, we'll take a look at a solution of sodium hydroxide. Sodium hydroxide is a strong base, so we expect it to be a strong electrolyte, and sure enough, the light bulb glows very brightly. All right, we'll rinse in DI water, and next we're going to make a couple of solutions. So here what I have is just some deionized water, and when I put the light bulb in, you see that it does not glow at all. And to this, I'm going to add some sodium chloride, or that's just table salt. Now, what do we know about the type of compound sodium chloride is? Is that an electrolyte? Is that an ionic compound? Is it a covalent compound? Since we've got a metal cation and a non-metal anion, this is a salt. This is an electrolyte. It's going to dissociate completely into Na plus and Cl minus because it's an ionic compound that's soluble in water. And what we see is that the light bulb glows very brightly upon adding the NaCl. Lastly, I'm going to make a sugar water solution. I'm going to start with just plain DI water, right? So this is not glowing at all. And to this, I'm going to add a spoonful of sugar. Now, sugar has a formula C6H12O6. So what type of a compound is that? Ionic or covalent? Right? This contains all nonmetals, and so this is going to be a covalent compound, meaning that there are no ions present. And so when I add this to water, it's a non-electrolyte. There are no ions in solution, and so it does not conduct electricity, and the light bulb does not turn on at all. It's nice to take a look at this demo and see the differences between different solutes and how some of them can act as strong or weak electrolytes, or some can even act as non-electrolytes and produce no ions in solution.